Alright, so for this video today we're going to be looking at we're going to do another video about we're going to look at resonance, and we're going to look at resonance and beats again. So December 6th. And I think at this late time of night, I think I'm actually just going to do just the resonance piece tonight. So, in class today, we looked at one like this. Okay, and the idea being is that when you do this, whether you do it with Laplace or whether you do r squared plus 25, you're going to get plus or minus 5i, which means you're going to get cosines of 5t plus sines of 5t, which then, of course, with constants here and here, excuse me, which means, of course, then you could combine this into one big C, cosine of 5t minus an alpha or some such. Plus, again, this is the complementary solution. Plus, you're going to get some, let's say, a cosine of 5t on this side as well for the particular solution. The idea being, when you add these guys, they have the same, so we call this the natural frequency. This 5t, this omega naught, we call it. We talk about that's its angular frequency. And this is 5 here, that's the driven frequency, the book will call it. When they are equal to one another, when they're equal to one another, and notice that we have no x double prime, because the value here in front of it, x prime rather, because c is equal to 0. When we have this, we have what's called pure resonance. There's nothing to stop it from moving. Okay? Now, going to the formula we've been talking about is this guy. Nose has been fine all day until, of course, right now. So, what I see here, this is mass times acceleration. That's a force. This is force. This is a restrictive force, so it works opposite the direction of the movement. This is the drag force, if you will. It's what we call the dampening force. And then, of course, this is your spring force. That's Hooke's law, right? F equals kx. These are all just forces, okay? And so the idea here is, when you have this situation and you have a dampening force in there, then obviously this is what drives everything. If you think about it, we did this earlier. We did r squared plus cr plus k. If we were to do it this way and say, well, all right, that's negative c plus or minus the square root of c squared minus 4mk over 2m. This guy right here really determines what happens. Obviously, if c is 0, then these are both positive constants. This ends up being a negative, yes? Okay. If c squared is equal to those guys, okay, then we're going to have one solution, right? With a double root. And if it's a double root, then it becomes something like this. We know x would be equal to, it'd be equal to what? Something like t, e to the t, e to the whatever, t plus something or another, e to the negative t, right? Or say e to the t, rather, right? Because it's the same value. Because it's the double root, right? So we know that. And then, of course, if c squared is bigger than those guys, all right, then we get two real solutions, and so we know it's e to the something t plus e to the something else t, right, with constants here and here, and that's great. Well, interestingly enough, we're interested pretty much only in the situation here where c squared is less than 4mk. Because what I really am interested in finding is getting some a plus or minus bi, which means I'm going to get e to the at Probably negative. Let's be honest, that's going to end up being a negative there. Okay. And then some sort of C1 cosine of BT plus C2 sine of BT, kind of a thing going on, yes? That's what I'm most interested in. And then I look at this inside piece and I say, well, wait a minute. This business in here could, of course, be written as some big C cosine of BT minus alpha, of course, yes? With this e to the negative AT with it, of course. This is the thing that we're most interested in, okay? This is where it gets interesting, okay? So, as a general rule, that's where it gets interesting, okay? Now, notice again that this is going to go away. This is what we call a transient solution. It's going away because it has an e to the negative AT in front of it. Okay? We know from the other side up here, if this was equal to some cosine of, whatever, omega t or whatever, then we know that there's going to be plus some a, cosine of omega t plus some b sine of omega t, right? And of course, these two people could be rewritten as some big D cosine of something like this, yes? Now notice that these guys, on this portion here, there is no e to the negative. So this is just going to do its thing forever and ever and ever. We call this the steady state solution. Pretty sure we've mentioned that before, just so we're clear on it though. Okay? So what we're going to be looking at today is, well, that's great. But in general, what if I take this piece right here? What if I were to do undetermined coefficients on this side over here? Okay, well, you're thinking, well, if I knew these guys and this guy and this guy, I could totally do that. I could find out, I know that my particular solution must be of the form a cosine omega t plus b sine omega t. We know that. And so that's what we're going to look at right now. We're not going to do it all the way out because, well, I don't know if there's any value in that. But, of course, we would start off with something that looks like this. So x prime, so p, the particular solution, of course, is negative a omega sine omega t plus b omega cosine omega t, and x double prime, of course, is equal to negative a omega squared cosine omega t minus b omega squared sine omega t, right? Right. And if I follow the rules, which of course said that mx double prime plus cx prime plus kx equals f naught cosine omega t, right? So if I take m times this fella, right? Now don't worry about it too much. We're going to cut to the chase here momentarily. Plus c times this mess plus k times the top one in your book always uses an f naught, just so we're clear. Alright, oh wait, it needs to equal that, right? But what is it? So what am I going to have this equal to? Well, I'm going to have it equal to a cosine omega t plus, oops, what am I doing? What are you doing? God, you're stupid. There we go. And so if you collect all your like terms and put all the cosines together and all the sines together, you will solve for a and b, and this is what you will find. The a is equal to this guy. And b is equal to this fella. Just like that. Okay? Now, that's always true. Always, 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 always. Okay? So that, what this means is you're going to have this fella here, F naught, K minus M squared, over this guy here, times the cosine of, what did I say, omega t, yes, plus this mess, right? Oh, but wait. Look at this. These are values in front of here and here. These really are just C1 and C2 kind of things, yes? Which means we can make a great big fatty C1 or something, well, not big C rather, I guess, cosine of omega t minus some alpha, right? And you're like, well, what is that big C, Mr. Groom? Well, glad to tell you. It's this guy right here. This big C is equal to F naught over the square root of 6. Why did I put 16 right there? Where did I write it? Well, I wrote it down somewhere, so I made notes to myself so I wouldn't do this. Then I go and schmuck it up. Come on. You put it here somewhere, dummy. There it is. I found it. Yay, I found it. Just a minute. Yeah, duh. K minus mu omega squared plus C omega squared. Yay. Now, what's interesting with this problem is this. There is an omega such that this whole fraction gets larger. Okay? So it has a maximum, in other words. Okay? And so what we're going to do is we're going to look into this in a little bit. Okay? Anyway, the idea here is it gets larger. This is what we call practical resonance. Okay? The idea is not pure resonance. They're not pushing with the exact same speed. That's not the point. But the point is this amplitude, which is this value in front right here, is going to be larger if this driving force, this driving frequency, is a particular frequency. Then we're going to get a particular increase in our amplitude, and that's going to show up when we do it. Now, again, when we play this game, you're going to see some interesting things happen here. Again, notice what happens if C is 0. Then this piece here cancels out. Yes, it would cancel out, and you'd be left with just this part right here. And it would be a constant, but the point is, it would just be it would not be slowing it down or hindering it in any way, shape, or form. Okay, so let's do one here. I happen to have made up one. You probably won't like it, but life goes on. So I want this one here, x double prime plus 2x prime plus 16x equal 10 cosine 3t. That's cool. And further, our first derivative and our initial conditions are both 0. So this is going to become s squared plus 2s plus 16 all times x of s, because there's no other parts, equal, and this of course is going to be 10s over s squared plus 9. I should probably look at my notes, but yeah, I'm good so far. And so what I end up with is 10s over s squared plus 9, s squared plus 2s plus 16 is equal to this fella. Now, I went ahead and expanded on my calculator, and I got the following. I got negative 14s minus 64 over s squared plus 2s plus 16. Now these were two separate fractions. I put them together for reasons that will become obvious momentarily, I hope. Something along these lines, yes? Now, okay, clearly this is cosine, so 14/17 cosine of 3t, obviously. And then, of course, this one is, well, this is a 3. You're going to put a 3 on top and a 3 on the bottom, which makes it 36/51st, which, of course, reduces, but I'm not in, this is not an Algebra 1 class, so whatever. Now, this one, this, I can complete the square in the basement, and I get this. You should check my math to see if I'm right, but I am. Which means that on top, you're going to have 14s plus 1, so like we did on the quiz the other day, which if you multiply that through, it's negative 14s minus 14. Well, negative 14 plus what is going to have to be this negative 64 that I have going on right here. Okay? And it would have to be minus 50. Yes? Because it has to add to negative 64. So negative 14 and negative 50 are there. So what I've got then is I've got a negative 14 s plus 1 over s plus 1 squared plus 15 minus 50, right, over, and then s plus 1 squared plus 15. Of course, we know what these are. These are negative 14 e to the negative t cosine square root of 15t. And of course, this is going to be negative 50 over the square root of 15 sine, oops, there's an e to the negative t right here, sine square root of 15t. Okay? Now, of course, we can combine these guys together and see what happens here. But when I do this, I'm just going to get, this plus this. And we can do that in a minute on our calculator. We can totally combine these guys in a second if we wanted to. Okay? We can combine these two and we can combine these two. Obviously, we can pull an e to the negative t out and then combine it inside. Okay? And I suppose we should do that momentarily. But let's go graph it first. I feel like that would be a better thing to do, a better use of my time right this moment. Boy, I wish I would have hit save earlier when I did this. Oh, well. What else am I going to do? It's only 11 o'clock. I'm no hurry to get to bed or anything, right? I mean, geez, why would I hustle? Right. So, negative 14 divided by 17. No, you hippie. Stop it. 17. I'm just going to go ahead and put cosine. When I'm all done, I'll go back and put the e to the t's out front if you don't mind. Oops. I forgot my square root of 15 in the basement down there. I'm not sure I wrote that on the previous page. We gotta make sure we get that figured out though. Sine square root of 15 x and then plus 14/17 cosine 3t and then plus 36 divided by 51 sine of square root of 15 x. What? Nice. Now, notice how we have a beat frequency going on. Do you see it? That's pretty cool. Okay? That's a pretty neat little beat frequency we got happening. However, and it's a big however, you have to be a little bit careful, okay? Because again, it's from here all the way over to here, right? Because this is only half of the period. Because see how the humps are on top up here and then they're on the bottom over here again? So, whatever, you can look at that later. That's not the important thing right now. But the reason it looks like that is because I didn't put a parentheses here and here. And put out front of that e to the negative x times. Okay? And what we see happening here, excuse me, we see it happening. We're fluctuating wildly on the negative side of things, and then it's petering out to look something like this. If I scroll out here far enough, something looks really funny. I'm going to go look at what I did wrong. Nope. That looks pretty good. It's pretty good. Pretty good. Okay. Did I drop something? Oh, that's why. Big dope. That should have been a 3. There we have it. Yay. Okay, so this is what should have happened, and it should have happened a lot sooner. There you go. See? It was going nuts over here, and then it peters out. And notice how it changes things initially. But pretty quickly, this first part with e to the negative x goes away. And look, you look at the peak of this guy, it's like 4.4. Well, if I was a betting man, what do you suppose? I'll do it right here. What do you suppose the square root of, parentheses, 14 divided by 17 squared plus, parentheses, 36 divided by 51 squared? What do you suppose that is? Oh my gosh, it's like 1.08, Mr. Groom. It is 1.08, but this is 1.095, Mr. Groom. You're crazy. Stick with me, yo. Notice how at the bottom down here it's down to negative 1.085. Stick with me. 1.083, 1.085, 1.083. You're like, what's going on? It feels like they're honing in on 1.085, 1.85, 1.8. Oh my gosh, what is 1.0846 round to? 1.085. So anyways, by the time we've gone through 3 or 4 cycles, we have gone to the point where this first part with e to the negative x completely canceled out. It's a pretty cool deal. Okay? Now, allow me to demonstrate something. You're like, sure, we didn't find on this last problem in there what value of omega would cause us to have practical resonance. And so the formula again is this fella. Now, by the way, interestingly enough, you want to have a maximum value of anything. What do? Why, you take a derivative, of course, Mr. Groom. So could we take the derivative of this? We could. I don't want to, but you totally could if you wanted to. I am going to pretend like I am, let's hypothetically, a kid in, let's say, a Patterson kid class. Why I could then simply, graph this on my calculator. And so I am using the values from the problem we just did and plugging them in. Our mass was 1 plus our C was 2 times omega squared. And when you graph this, interestingly enough, let's see what happens. Now, what I'm going to do, shut that off for a minute. I'm going to type in 10 divided by the square root of, and I'm going to do 16 minus, but check it out, dog, I'm going to put in an A. Squared. Oops. No. Squared. Plus, parentheses, and then I'm going to put in 2 times A square, like so, and put a slider to that thing. Now, look what happens. Okay, so when A is 1, you get this thing. But now, why is that not graphing? Oh, never mind. Duh. Let's try it again, stupid. It's getting tiring, you can tell, because I'm not paying attention to myself. There we go. There we go. It's gonna work now. What in the devil did I do? Square root. Oh, there's the problem. Do you see the problem, friends? Because there should be another square root, right? Another parentheses right there. And finish the parentheses here. They weren't in the square root anymore. That was freaking me out, man. It was like totally weirding me out, dog. What? What? Okay, now I'm just getting pissed off. Plus, how it's starting to look like it's supposed to look, for crying out loud. That's what I'm talking about, dog. Nice. So when x is 2, which it is in our problem, okay, we would have a maximum that would occur right here. So when we had an omega of 3.74, we would have a maximum amplitude of 1.29. Okay, that's what we're saying here. So 1.29 would be the maximum amount of amplitude. Well, what do you mean, Jay? Or rather, Mr. Groom. So if you come back over here to this fellow, okay, here, 1.29. Oops, where did they go? Where did they go? What happened here? Okay. So that's what ends up happening here. So in the case of ours, we were driving it at, I shouldn't say that was what would happen if we were driving it at if we were driving it at 3.74, that's what we would get. In other words, come back here. So at 3.74, we would get a maximum amplitude. We weren't driving, we were driving it with a force of 3. So if you drive over here, pull it over here, 3, 1.085 is our amplitude. That's exactly what we said it should be. Now you're like, well, what if I had 0 right there? What? Look at that, friends. What do we see? We see what we call what? Perfect resonance. Pure resonance. And that happens when our driving force is, and that's 4 for all intents and purposes, okay? So don't sweat that. Alright, now, we know that's true. That's because we have no dampening. That is, we're driving it with the same amount. There's no dampening. If we drive it with a force of 4, with a frequency of 4, we'll get pure resonance. It's a pretty cool deal. Now, again, let's bring it up here a ways. Okay. Now, what happens if I drive it too fast? At some point, I will drive it too fast. You see, and I will get beyond. If I have too much dampening force, I will have no resonance at all. Okay. If you keep going, what happens here? Okay, it just gets up here and that doesn't do anything. So at some point, right in there somewhere, it goes to 0. And again, why does it go to 0 right there? Well, let's think about that for a minute. 0.625. So let's go back to our thing, and we said it was 1r squared plus 2r plus 16 equal a goose egg, -2 plus or minus the square root of 4 minus 4ac, which is 64, all over 2a, which is 2, so it's -2 plus or minus the square root of 60 over 2, which is -2 plus or minus 2 root 15 over 2. Okay. Now, when we look at that situation there, what are we saying? Oops. We're saying this 6.5 thing is when we kind of run out of. It looks like somewhere right around that 6.5 is where we run out, maybe 6-ish. So let's come back here and let's, instead of putting in that value, let's put in just a b term here. All right. So let's see, what does that give us there? So b minus 64, or b squared minus 64, it looks like when b squared is equal to 64, what's going to happen? That's when we're going to have our one solution deal, right? So let's see if we can see what's going on here. This is when we are at 5.9. So somewhere in the 6-ish range, 5.9-ish range is where we tend to lose out. So we're going to talk some more about this. This is the idea of, suppose we're changing this stuff up, what happens? Where does it happen? It's very similar to bifurcation we did earlier, in that if you're changing one aspect of the function, how is that relating to what's going on here? Okay, how does that tweak it out? Now, at this point, you're like, well, you're trying to solve this, Mr. Groom. That's true, I am. But in reality, what I should be trying to solve is up here somewhere, right? Because at some point, what's going to be happening to this guy is what goes on around 6. Okay? So, let's actually take the derivative of this amplitude instead. So if you take the derivative of this amplitude, of course the derivative of the top is just 0, so that's cool. Minus, so it's the top times the derivative of the bottom, which would be a half. Who am I kidding? This is America. This is the 21st century. I'm going to get my freaking calculator out. Because I can. I'm a freaking teacher. That's why I can do it. I'm tired, so tired, as we dream by fire. Alright, so if I take the derivative of 10, yeah, I'm just going to do the derivative of this guy. We can do it in general. I think I want to do it this way for right now. Oops. The derivative of the square root of 16 minus x squared plus, and then I'm going to use z times x squared with respect to x. Boom. Cool. And then what I'm going to do is I'm going to say, alright, solve. I'm going to set this baby equal to 0. And I'm going to solve for x. Is that what I want to do? No, I don't want to solve for x. I want to solve for... It would be okay to solve for x, but there it is. Okay. So these are the values of x. Okay. And so then, of course, if you plug in 2, for instance, that's pretty interesting. You're going to see some values that will come out of there that would be pretty interesting to us. So, for instance, I bet that comes out to be 3.74. Let me pause for a moment. Okay, I just plugged in z equals 2, and lo and behold, there's our maximum. I don't think anybody's shocked by that. Anyway, we'll pick up a little bit more tomorrow in terms of what else to talk about when that thing stops. But the big thing what I'm going to have you do is when you're looking at a graph is clearly you can tell that when A, which is our drag, increases up to about 5.9 or so, we lose the resonance. And again, resonance happens. You can see it happening, that peak. Whee! Wherever that peak occurs, you see this is when we have a C value of 2.3, then our driving force, if it matched 3.65 or thereabouts, we would have resonance. If it's not near there, we're not going to have resonance. And of course, this is what our new, what you call it, amplitude would be. So what I ended up doing, because, well, that's what I do. Put it back to 2. And notice it says if you drive it at 3.742, we should achieve this asymptote. Or not asymptote, amplitude. So, I went ahead and did it that way. I said, well, alright, well, let's just change it up. So I switched it around and said, well, same exact formula. But this time, let's drive it with this formula, 3.74t. What? So of course we know that it's going to be x of s is equal to, this of course is going to be 10s over s squared plus, it turns out to be about 13.98 when you square them, this thing squared, and then of course divided by s squared plus 2s plus 16. And when you expand that out, you will get negative 0.336 s minus 5.33, think, over s plus 1 squared plus 15, and then plus 0.3364 cosine 3.74 t plus 4.66 over, well, kind of 3.74. I kind of cheated on this piece. Okay, well, I didn't write this part down, so I cut to the chase on this side. So don't panic about that. And then I took this piece and combined them, and I got that this was 1.29 cosine of 3.74 t minus 1.306. Again, I did that by taking this guy squared plus this guy squared, square rooted, dividing it through, which was 1.29. So I put that out front, divide it through here. Great. Inverse tangent of this guy over this guy came out to be 1.306. But remember, it's alpha. It's this business minus alpha. So there it was. Okay, because it's a positive right here. And then this side over here, as I wrote it out as there's an s there. Negative 0.33655 s plus 1. And if you distribute this out, you will see that you need to have a negative 4.994 or something here. And so this piece becomes negative 0.33655, whatever, cosine of square root of 15t. And then, of course, this becomes minus 4.9. Well, my calculator in front of me. Darn it. Well, I want to say this is 4.9 because if you take this times this, that's negative 0.3. And negative 0.3 plus this is negative that. So this is what I had. This is what I need. I wrote my notes down funny. It should be this over square root of 15. And it's going to be sine square root of 15t. And of course, both of these get hit with e to the negative t, right? And I didn't go ahead and collect these two together. I didn't, but if I wanted to, I totally could have. But let's look at the actual graph of this thing. Okay. Now we know that all I have to do really is come in here and change these pieces. So I'm just going to do that. So I feel like that's the easiest way to do it. And so it's negative 0.3365 or something. Oops. Darn it. Okay, and then this piece here is 4.99 or something divided by the square root of 15. And then this piece just becomes, let's lose some of this mess. And then it becomes minus. And this is not that. Oops. Plus. Nice. Turn it on. Okay. What? First of all, let's get a decent frickin'. This is disturbing. Why is it doing that? Again, notice at the first it's affected. But look what's happening to our amplitudes. There they are. Look what that amplitude is. Okay, 1.302, 1.29. Let's keep going. 1.29, 1.28, 1.29, 1.29. And what happens over time, friends, is they all become 1.29. And that is what this graph is showing us wherever it went. Oh yeah, right here. So this is showing us this bit right here, you see, becomes the deal. Now, 1.29, Mr. Groom, I thought we saw that from somewhere else. Well, we did see it from somewhere else. We saw it right here. Right here. When we had a driving frequency of 3.742, we will see a steady state amplitude of 1.29. That's what we're going for. Okay? So the long and the short of it is this. Whenever you see a situation where you have some x double prime plus some x primes plus some x's equaling some sort of a sine or cosine function. It could be either one, doesn't really matter. Okay? Simply take these values, which again are m, c, and k, this fella here and of course this fella here, and plug them into this formula. Okay, plug it into this formula, and when solve for the value of omega, it will give this thing a maximum. Okay, and then from that, what you're going to find is that's what's called practical resonance. And again, we had some initially in this function. You notice we had some constructive and destructive interference at first. Now it's possible that you could have it driven such that right off the bat, based on where it starts from, that you could have some interference or some constructive and destructive interference that actually causes things to shatter apart. But notice that over time, our e to the negative x part, our transient solution, cancels out. And again, we are left with just this steady state piece coming through the thing. Okay? That's about it. Now, of course, if this comes down here to, or it comes up here to about, I don't know, let's just say, let's overshoot this thing a little bit. Let's come back here and take a look at the graph. So we set it right around 5.9, but let's actually do it a little bit more. Let's go to a nice value like, say, 6, for instance. Suppose our driving frequency were 6. Oh, well, I wonder what that would do for us. Okay? So if our driving frequency were 6, so I'll just do it with the formula that we had. Or no, rather this piece here was 6. So if this were true, then what would end up happening here? Well, this would end up being, of course, x double prime plus 6x prime plus 16x equal. Now what's going to happen over here? Well, this was just 10, and then this would be s. Well, I'll go ahead and write it out. I'll just leave it this way first. 10 cosine. Now, what we said was if this was 6, then, you know, I'm just going to let this be. This was, what did we say it was the first time? 3, I guess, t for fun. But let's see what happens on this side. So if you're going to do it the old school way, you do r squared plus 6r plus 16. So that's negative 6 plus or minus the square root of. And of course this becomes 36 minus 64. And this becomes what? Well, that's negative 28. Negative 6 plus or minus. And so, of course, over 2. But what's going to happen here is this. Okay? When I have this situation here, look at this piece right here. Look what's happening to that guy. This is going to be e to the negative 3t. And yeah, you're going to have some cosines and some cosine and sines in here, right? Obviously. But what's happening to this piece right here? It is canceling out so fast that you will not see any practical resonance. In fact, right off the bat, you're pretty much going to see the steady state solution almost immediately on this problem. Okay? Now, I guess I will go ahead and figure this out. So it's going to be e to the negative 3t, and then it's going to be, of course, c1 cosine square root of 28. I'm going to get a decimal for that, if that's okay with you. Square root of 28. Yes, I know it's 2 root 7. 5.29-ish or something. 5.29t. And then, I don't know why I'm doing it this way. I guess it doesn't matter, though. It's whatever. C2 sine 5.29t. Okay. I know that's what it's going to come out with. And I know I'm going to end up with some, and I'm just going to say some sine or cosine over on this side. Okay. Yeah, what the heck. You know, I'm just going to do a cosine. I'm going to go ahead and do it this way just for fun. Plus b sine 3t. Just to practice, I guess. Just to see if I can still do it. So we know our cosines, which are, and I've got one of them. So I've got one of the double primes. We got negative 9a minus 3b. These are cosine. This is sine. It's a 9, dummy. And then I've got 6 of the middle ones. So minus 18a sine plus 18b cosine. And then I've got 16 of the last one, so plus 16 cosines with an A, and plus 16b sines needs to equal 10 cosines. Okay? So negative 9a plus 18b plus 16a equals 10 cosine, equals 10 rather. And negative 9b plus minus 18a plus 16b equals a goose egg. So negative 18a plus 7b equals 0. And negative 7a plus 18b equals 10. So if I don't know, you can do it a couple of ways, I guess. It's about 6 1 half a dozen the other. Maybe I times the top one by negative 7 and the bottom one by positive 18, I guess, because why not? Why wouldn't you do that? 18 times 7 is 126, right? A minus 49b equals 0. Negative 126a plus 324b equals 180. If you add now, you will get, I can't do that in my head. That's 15, 27, I think, 275. Oh. Really? Stupid computer. So B is that. Why did I do it that way? That was really dumb. You have a calculator. Why don't you just solve it? It's only 5 minutes till midnight. Why can't you do math in your head? What's your problem, Mr. Groom, you big dope? There it is. 14 over 55 and 36 over 55. Okay. Alright, and then of course if I knew my initial conditions I would plug them in. What I really want you to see is it doesn't make a whale of a difference. Because look what happens. If I make this e to the negative 3x right there, I don't really care what you put here or here. This thing is dropping to 0 so fast it's going to make your eyes bug out. Okay? Now, what did we say our value was? We said it was 5.29 for those values. Let's go ahead and put those in there. And again, I don't really care. I'll just leave that alone. It's not going to hurt anything because it's going to 0 so fast. And then the second part of the equation we said was we didn't combine them yet. Oh, we could. I'm not going to this time. Was 1455 cosine 3x, and then of course 36 over 55. Nice. And so what we end up with is there's really no resonance at all. It's just boom, 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 and away we go. And notice how it's within one period, you've pretty much got to your peak and then you're done. So it's basically less than one period, you're back to where is that steady state solution across there. Okay. Now, again, this is one where we said it was about 6. When we did that earlier on the other thing, we said it wouldn't do resonate, it wouldn't have a maximum. And again, that's because, I wish I hadn't have deleted that, but I guess I'll put it back. It's the last thing I want to talk about here. Okay. Now, again, it's the same problem, so it's not going to change in terms of when this thing changes and you get around 6, somewhere on that 6 point, there's no longer a hump here. So you can find a maximum, and you'll see a maximum here, right? But when you drag it over towards 6, that maximum goes away. And so that's obviously the point is if you drove it at 0, you'd have, the 0. That's when you'd have the most, okay? But we're not driving it at 0. We're driving it at a particular value. So if we come out here, and we say, well, we're driving it with a frequency of 3, is what I said. Of course, it's not going to be that value. It would be that value if we'd filled in all these blanks. The reason it's different is we didn't bother to fill in these guys. Okay, that's why it's a little different. Okay. All right, we'll do more with it. That's just, again, this is our second day of this. We're going to do more with it. It's going to take time to get it all down.